All right, so here we have an exercise that's sort of similar to the minimum swaps exercise, um, but it's different. Here, people start out they're lined up 1 through 8 or 1 through n, and you can bribe someone to take their spot. Um, And so it's sort of like the swaps, but there are some additional rules here. Specifically, you can only swap with someone who is one next to you. And specifically, if you can only swap with someone who is ahead of you in line. And you can only swap twice. And so this sort of makes things a little bit difficult because you have to think about, okay, where are the first of all, again, they're looking for the minimum number of swaps um, that would have been made to go from the initial ordering to whatever ordering is given to you. Um, and so you have to think about, okay, what is the optimal strategy and how do we count it? But then there's also here you have to figure out, is this output even possible? Um, so let's see here. I guess a good way to think about this is to just sort of look through some examples. And so you can sort of, if you have a good idea of how to go about solving this problem, you can skip ahead. But I just want to sort of show how you would go about coming up with this problem if you didn't know in the first place. So let's see, I think one of the examples, it was like 1, 2, 5, 3, 7, 8, 6, 4. And even just looking at this, you can sort of see this idea of 4 is way off from where it should be. But how do you... so things are sort of restricted in how far they can go, so how could it get there? Well, a bunch of people must have swapped places with 4. So let's go through and let's first just see if we can just put things in order one by one, and then we'll think about if that's a good idea. So 1's good, 2 is good, 3 is not good, so let's switch that. So again, we're working backwards here. So what we're doing is we're assuming that in the previous step, what happened was 5 swapped places with 3. So 5 bribed 3 in the first, in the second to last step here. Then in the step before that, let's see here, we got to move 4 all the way back. So 1, 2, 3, 5, 7, 8, 4, 6. So what will have happened here is 6 must have bribed 4. Then getting 4 a little bit closer, here 8 would have bribed 4. 1, 2, 3, 5, 4, 7, 8, 6. Here 7 would bribe 4. Then 1, 2, 3, 4, 5, 7, 8, 6. And here 5 bribed 4. So now it's only 7, 8, and 6 which are out of place. So going next up to 6, so let's see here, 7, 6, 8, to bring 6 a little bit closer. So here in this step, 8 bribed 6, and then 3, 4, 5, 6, 7, 8. Here, 7 bribed 6, and we're back to the initial ordering. Okay, so how many steps did we have here? We had 7 steps. Okay, so we're thinking that that's the minimum number. Now, first of all, is this possible? And just looking at this, the way we think about that is we look at this column of who was doing the bribing. And we see that no person made more than 2 bribes. And so for that reason, this is possible to do. But another way to think about that would be, okay, so if you make more than 2 bribes, then you end up more than 2 spaces ahead of where you started. So if we see here, like for 5, for example, 5 ended up in the 3 index. So it was exactly 2 places ahead of where it started, so it must have made 2 bribes. So as we're going through this list, it's pretty easy to check if the scenario should be labeled too chaotic, because if an index is more than 2 spaces ahead of where it started, then it's too chaotic. Now, you can see that a person can be more than 2 places behind where they started, as we see 4 is way behind where it started, but that's just because 4 received bribes rather than gave bribes. And so let's see here. In order to count the number of bribes, or count the number of swaps that was needed, of course we have 7. But if we think about like what we're seeing here, so what's a better way? It would be really nice if we could figure out a way to undo these swaps where we don't have to actually keep track of all the swapping around. If we could just sort of look at this list and be able to count from this list how many swaps must have been made, that would be ideal. And it would make our code run faster. So what we can do is we can sort of look at this column now. These are the recipients of bribes. And so, for example, we see that the number 4 received 4 bribes. And sort of, how can we think about that? So we know 4 started here at this index. And so who did they receive bribes from? From 5, 6, 7, and 8. And we see that these 5, 6, 7, and 8 all appear here. So the way that you can count, and this sort of makes sense because let's see here. So in the case of 5, so why are we starting? So this dot that I marked is where 4 started. Why have I started? Why does my bracket of where I've looked for these things, why does that go 1 to the left of the dot? Well, if you think about it, 4 could only have received bribes from person 5 or above. And what's the furthest left a person 5 or above could go relative to where 4 started? The worst case scenario would be that the person 1 spot to the right of 4 used 2 bribes to move 2 spots to the left, ending up 1 spot to the left of where 4 started. And so that's why this bracket that I've drawn starts 1 to the left of where 4 started. And of course it ends at just to the left of where 4 is now. Because, of course, these are the only people who would have bribed 4. Because if you bribe 4, then you go before 4. So here are the conditions for testing if, let's see here. So, person PQ. Person Q has bribed person P if Q is greater than P and Q ends up in an index between P's original index minus 1 and P's current index minus 1. And of course that minus 1 there for the current index doesn't really matter, because if you include P's current index, well, P is in P's current index. So if you check that as well, then that doesn't, Q is never going to be there. So that's sort of specifying where this bracket that I've drawn. So like here for this example that I've drawn, we have Q equals 4 no, Q has bribed person P. So Q equals 5, P equals 4, and Q equals 5 ends up between indices. Let's see here. P's original index was 4, so 4 minus 1 was 3. And P's new index is 8 minus 1 is 7. So basically, Q ends up between indices 3 and 7. So who else swapped with 4? Well, if we just look at this list, so we look at every person whose number is greater than 4 and who appears between 3 and 7. So we've got 5, 6, 7, and 8. And if we look at our column that we've drawn here, that's exactly the people who swapped with person 4. Okay, so what do we know? So that gives us a way of determining how many bribes person 4 received just by looking at the list itself. Okay, so now with that in mind, that gives us an algorithm for counting the number of swaps, because you go through each person and you count how many bribes did they receive. And so in this example, we can see person 4 received 4 bribes, 3 received 1, and 6 received 2. And that's how you get your solution. Now, there is a question here of, is this the optimal way? Because remember, this is minimum swaps. We're looking for the minimum number of swaps that would have been required. Well, our strategy here is to correct these people one by one. So we corrected 1 and 2. Well, 1 and 2 were in the correct places. Then we corrected 3. Then we corrected 4, etc. So what would happen if there was a better way to do this? Let's say that instead of correcting 3 at the beginning, there was another swap that you could have made. Well, whatever swap you could have made could have been made after correcting for 3. Because basically what you have is after you correct 3, you've got a jumbled subset between 4 and 8. And the order of these is the same that it was before you corrected 3. And so any swaps you could have made, other than correcting 3, would have just jumbled those indices 4 through 8, which you could just do after correcting 3. The only scenario in which you couldn't do that afterwards would be if you moved 3 further away than where it needs to be, in which case you're actually de-optimizing the process. And so through this line of thinking, you can sort of convince yourself that correcting these indices one by one is the correct solution. All right, so that's sort of how we go through and think about this problem and how we come up with a solution. So let's actually code it out now. Okay, and again, so let's go through here. And again, I need to credit this code comes from a comment. And this comes from, if you just go into the discussion section, I was able to find this because I did get a little bit tripped up on thinking about what the best way to approach this would be. But here we go. And actually, the comment does a really good job of describing the thought process, more than some of the other comments that I see. But it's basically what I explained in fewer words. But it's also written, which I personally like when someone explains things to me in words rather than reading text, but just a personal preference. Anyway, so we're going to count the move, and we're going to start at 0. The first thing we're going to do is we're going to decrease Q by 1 to make indexing easier. Because again, the indexes start at 0, and that gets a little confusing. So we're going to set Q equal to P minus 1 for P in Q. So capital Q is just lowercase q, but shifted over 1. Okay, so now loop through each person P in the queue. So I'm guessing that this commenter is British since they've got chat and since they're talking about queues, but whatever. This is also sort of better terminology than just thinking about a list. Also, maybe they used Q in the problem statement. I don't know. Anyways, so for I and P in enumerate Q. So again, we're using the enumerate here just like we did in the other one. So this seems to be a really common tool for these sorts of problems. Okay, so remember, I is the current position of person P, while P is their, P is their original position. All right. So I'm just thinking about that because it's sort of, so P is referring to the original position of person P. That seems a little, let me double check that. We'll actually go through and look at the original. Yeah, well, I is their current position and P is their original position. All right, so what we're going to do is check if person P is too far ahead of where they started. So if P minus I is greater than 2, then we print out 2 chaotic. And then we return since we're done. So right, we have to check in. So P, remember P is the person's current position. And I is their initial position. So if their current position minus their initial position is greater than 2, right, because if we remember that example from before, 5 was in 3's position, so P would be 3 and I would be 5. So 3 minus 5. Wait, no. I have it backwards. I is the current position and P is the original position. There we go. So P, check if person P is too far ahead of where they started. So if their original position minus their current position. So in our example from before, 5 was in the 3 position. So their original position, or their original position was 5, and their current position was 3. 5 minus 3 is 2, and 2 is not greater than 2, so it's good. It would only be if 5 were in the 2 position, because then you'd have 5 minus 2, which is too big. Okay, cool. All right. So then count the number of bribes person P received. Again, this using person P, it seems sort of confusing because we're using P to refer to the original index of P. So anyways, for J in range max P minus 1, 0 to I, if Q J is greater than P, then we increase the moves by 1. Okay, and that's about it. Okay, so let's go back and talk about this. So let's first start with this. So remember, if we want to figure out how many bribes a person received, we go to their starting index minus 1 up to where they are now and see how many indices do you have that are greater than P. So here, J is ranging from P minus 1, so that's the original index of person P, minus 1, so that's good. And then it goes up to I, which I think in this scenario means that it would go up to index I plus 1. No, it would go up to index I minus 1. But that doesn't really matter here because, again, person P is going to be in index I, so you don't need to go all the way up to index I. Going up to index I minus 1 is fine. Okay, so, and then for all of these, all the indices in this range, you just check if, so Q of J will be whatever value is currently there. So if the person currently in this index has a value greater than P, then that person must have bribed P at some point. And so you increase the number of moves by 1. All right, so count the number of bribes P received. Now there is a difficulty here because you have the issue of what if you're looking at person. Okay, so remember we decreased Q by 1 to make indexing easier. So the indexing starts at 0 now. So there is a scenario where P is 0, in which case we're asking it to start at, this can ask the code to look at the -1 index of Q, which doesn't exist because Q starts at 0. So we want to make sure that we don't go, that we don't look to the left if there is nothing to the left. And so that's why we do the max of this value and 0 to make sure that we don't ask it to look up a negative index. All right, so now we go ahead and we just run the code and it seems to work. So we go ahead and submit it and it runs all the cases pretty quickly, and there we go. So yeah, I think that the most difficult parts for this problem is really just sitting down with the original untangling problem and really just working something out by hand and really understanding how it works. And once you see that, you can start to get a good idea of, okay, first of all, what is the best algorithm for counting the minimal number of swaps? How do I know for sure that this is the optimal strategy? And furthermore, how do I implement this? And because we were able to implement it just by looking at the list, we were able to implement it without actually swapping around anything in this array, which is really good because that's probably what would have taken up the most time and could have possibly caused this thing to time out, because if you recall, for some of the test cases, these arrays are quite large. And so, yeah, it's really just a matter of understanding what you want to do, and then actually implementing it, we can see, doesn't end up being that difficult. This is more about understanding the problem itself than understanding how to implement the solution. Or it's more about it's more about coming up with the solution itself rather than implementing the solution. The implementation is on the easier side. So there you go. That's how you go through solving this problem, and that's about all there is to it.